17 hours ago, 8 billion tons of superheated plasma left the Sun's surface, traveling at 2,000 kilometers per second. In 14 minutes, it will hit Earth's magnetic field, and there is nothing anyone can do. The satellites will go first. GPS signals scatter, then vanish. Airline pilots lose navigation over the Atlantic. Then the power grid. Transformers across 3 continents overload simultaneously, melting components that take 2 years to manufacture. Hospital backup generators have 8 hours of fuel. Traffic lights, water pumps, bank networks, everything connected to everything else cascade into darkness. The estimated economic damage reaches into the trillions. And the strangest part? This has already happened. Not the civilization-ending version, not yet, but it's coming. This isn't speculation, it's physics, and the physics is remarkably simple once you see it. Here's the conceptual spine that explains everything from auroras to blackouts. Charged particles spiral along magnetic field lines. When magnetic fields collide and reconnect, they release enormous energy. That's it. That single principle governs every phenomenon in space weather, the invisible storms that could, on the wrong day, send human civilization back to the 19th century. The Sun isn't a steady lamp, it's a continuously exploding thermonuclear furnace with a surface temperature of 5,500 degrees and a core temperature of 15 million. Hydrogen atoms slam together with such violence that they fuse into helium, releasing energy that takes 100,000 years to random walk its way from the core to the surface. But the Sun's magnetic field, that's where the chaos lives. Magnetic field lines thread through the solar plasma, twisting and tangling as different latitudes rotate at different speeds. Eventually, these field lines snap and reconnect explosively. That's a solar flare, a flash of X-rays and ultraviolet radiation that reaches Earth in 8 minutes. But the flare is just the announcement. The real threat follows. A coronal mass ejection, or CME, a bubble of magnetized plasma containing billions of tons of charged particles racing through space at anywhere from 400 to 3,000 kilometers per second. On September 1, 1859, a British astronomer named Richard Carrington was doing something that would seem suicidal today, projecting an image of the Sun onto a white screen and sketching sunspots by hand. Sunspots had been known for centuries, darker, cooler regions where intense magnetic fields inhibit convection. But at 11:18 that morning, Carrington witnessed something no one had ever documented. 2 brilliant points of white light appeared near a large sunspot group, intensified over 5 minutes, then faded. He had seen a solar flare, the first one ever recorded. Carrington noted the time carefully, suspecting something unusual might follow. He had no way of knowing that humanity's first encounter with space weather had just begun. 17 hours later, the sky caught fire. Auroras, normally confined to polar regions, blazed over Cuba, Hawaii, Colombia. In New York, people read newspapers at midnight by the light of the crimson sky. Rocky Mountain gold miners woke at 1 in the morning, convinced dawn had arrived. But the real strangeness happened to the telegraph network, the only electrical infrastructure that existed. Operators reported sparks leaping from their equipment. Some received shocks. Fires broke out at several stations, and then something impossible. Operators in Boston and Portland disconnected their batteries entirely, yet continued sending messages. The geomagnetic storm had induced enough current in the telegraph wires to power the system on its own. The atmosphere itself had become a battery. Here's what happened and why it matters now. When the CME from Carrington's flare reached Earth, it slammed into the magnetosphere, the protective magnetic bubble generated by Earth's liquid iron core. Charged particles can't cross magnetic field lines easily. They spiral around them, trapped. That's why the magnetosphere normally deflects the solar wind. But a CME carries its own magnetic field. When the CME's field points opposite to Earth's, when it's oriented southward, the two fields can connect and reconnect violently. This is magnetic reconnection, and it dumps enormous energy into Earth's magnetic environment. Charged particles that were deflected now have a pathway in. They funnel down along field lines toward the poles, colliding with nitrogen and oxygen in the upper atmosphere, exciting those atoms, which then emit light as they relax. That's the aurora. Beautiful, yes, but also a warning sign. The same process that creates the light show creates something else, rapidly fluctuating magnetic fields at ground level. And fluctuating magnetic fields, as Faraday discovered, induce electric currents. In 1859, the only wires were telegraph lines. Today, there are millions of kilometers of power transmission lines, pipelines, undersea cables, and railway tracks. All of them are conductors. All of them can carry geomagnetically induced currents. And this is where the danger scales beyond anything Carrington could have imagined. Power grids weren't designed for geomagnetically induced currents, GICs. Transformers are built to handle alternating current at precisely 50 or 60 Hz. GICs are quasi-DC. They vary over minutes, not milliseconds. This DC component saturates the transformer core, pushing it into a non-linear regime where it no longer transforms voltage efficiently. Instead, it generates heat, a lot of heat, and harmonics, distortions in the current waveform that propagate through the network, causing protective relays to trip, capacitor banks to fail, and other transformers to overload. One damaged transformer can cascade into regional blackout in minutes. This isn't theoretical. On March 13, 1989, a geomagnetic storm far weaker than the Carrington event hit Earth. Within 90 seconds, the entire province of Quebec lost power, 6 million people in darkness. The Hydro-Quebec grid collapsed not because one thing failed, but because everything failed together. Protective systems tripping, capacitors overloading, transformers saturating. The storm wasn't even particularly severe by historical standards. It measured about a negative 450 on the Disturbance Storm Time Index. The Carrington event likely reached negative 1600 or worse. Scale that up. The most terrifying vulnerability isn't the blackout itself, it's the transformers. Extra high voltage transformers are custom-built behemoths weighing hundreds of tons. There's no global stockpile. Manufacturing one takes 12 to 18 months. If a Carrington-class event destroyed a significant fraction of the transformers in the developed world simultaneously, replacement wouldn't be a matter of weeks, it would be years. And in those years, everything that depends on electricity, which is now everything, stops. Satellites face a different version of the same physics. In geosynchronous orbit, 35,000 kilometers up, spacecraft live outside the protective shield of the magnetosphere much of the time. During a geomagnetic storm, the radiation environment intensifies dramatically. Energetic particles penetrate electronics, flipping bits in computer memory, single-event upsets that can crash systems or corrupt data. Worse, accumulated radiation degrades solar panels and sensors over time. The Halloween storms of 2003 knocked out or damaged over a dozen satellites. Japan's ADEOS-2 environmental satellite was destroyed outright. GPS accuracy degraded for days. Airlines rerouted flights away from polar regions because high-frequency radio communication, their backup navigation system, was overwhelmed by radio blackouts caused by solar X-rays. But there's a third category of consequence that's harder to quantify: human life in space. The International Space Station orbits within Earth's magnetosphere, mostly protected. Astronauts retreat to more shielded areas during solar particle events. But future missions to the Moon, to Mars, will operate far beyond that protection. The journey to Mars takes 6 to 9 months. A major solar particle event during transit would expose astronauts to potentially lethal radiation doses in hours. Space weather forecasting isn't just about protecting power grids, it's about whether humans can survive in deep space at all. So what are the odds? Solar activity follows an 11-year cycle driven by the gradual reversal and regeneration of the Sun's magnetic field. During solar maximum, the active peak, sunspots multiply, flares intensify, and CME frequency increases. 2024 and 2025 mark the current solar maximum. But here's the counterintuitive part. The biggest storms don't always occur at maximum. The Carrington event happened during a moderate cycle. The 1989 Quebec storm occurred during the declining phase. What matters isn't the average activity level, it's whether a particularly active region happens to be facing Earth when it erupts. Researchers estimate that a Carrington-class event has roughly a 10 to 12% chance of occurring per decade. Over a 50-year period, the probability approaches 40%. Over a human lifetime, it becomes more than likely than not. And unlike earthquakes or hurricanes, there's no gradual warning. A CME launched from the Sun can reach Earth in as little as 15 hours. Current monitoring satellites, primarily NOAA's Discover spacecraft at the L1 Lagrange point, 1.5 million kilometers sunward, can detect an incoming CME about 30 to 60 minutes before it arrives. That's enough time to alert power grid operators. It's not enough time to do much about it. The defenses being developed are procedural, not physical. Grid operators can reduce power flow during warnings, bringing transformers out of saturation range. Satellites can be put into safe mode. Airlines can reroute. But these measures require accurate forecasting, and space weather prediction remains in its infancy compared to terrestrial meteorology. The physics is known, the Sun's behavior is not. Magnetic reconnection is sensitive to conditions scientists can't yet measure remotely. There's something almost philosophical in this vulnerability. For 4.5 billion years, the Sun has been the source of all energy that sustains life on Earth. Photosynthesis captures its light. The hydrological cycle runs on its heat. Without the Sun, everything dies in weeks. But the same Sun that gives life also occasionally sneezes, ejecting more energy in a few minutes than human civilization has used in its entire existence. And in the century since humans built a global electrical infrastructure, the Sun has been unusually quiet. The Carrington event occurred before electricity mattered. The storms since have been manageable. But there's no physical reason this quiet period should continue. Stand outside on a clear night and look up. You're seeing through the atmosphere, past the magnetosphere, out into a solar system bathed in the solar wind, a 1,000,000-mile-per-hour flow of charged particles that has been blowing continuously for 4.5 billion years. Earth floats in that wind like a rock in a stream, its magnetic field deflecting the flow around it, maintaining a cavity of relative calm. That cavity is all that stands between you and the void. It's invisible, it's intangible, and on the wrong day, it can be breached. The physics that governs space weather is beautiful in its simplicity. Charged particles spiral along field lines. Magnetic reconnection releases energy when fields collide. These principles explain auroras over Norway and transformer fires in Quebec. They explain why astronauts shelter during solar storms and why GPS sometimes lies. They explain how telegraph operators in 1859 witnessed the first glimpse of a threat that now holds civilization hostage. The sun will erupt again. The only questions are when and whether we'll be ready. Like if this was interesting, hit the subscribe for more and turn that notification bell on.